I'm Citily Brown. I am in Biosystems Engineering, and I'm the team lead for our project, and we are Team UroSMART.
Don't mind me. I'm Jesus Lopez. I'm a biomedical engineer, and I'm the procurement lead.
Hey guys, my name is Sajani Adu. I'm a biomedical engineering major, and I'm the front development end lead.
Oh, hey, I didn't see you there. My name is Samuel Beaver, and I am the electrical computer engineer, and I'm the electrical lead.
3, 2, 1.
Hey!
I'm Abdul Hassan. I'm in the industrial engineering, and I'm the quality control lead. Accurate hearing and monitoring is essential for a patient with kidney and neurological condition, but current methods rely on mechanical measurement that time-consuming and prone to error. Our solution changes that by using a low sensor and an IV stand with a clamp, track of urine flow and bladder volume, and transmitting the data to the mobile application. This gives the patient and the healthcare providers an instant access to reliable information. This reduces the workload and saves time and give more accurate results.
Okay, so right now what we're doing, after we did our first run with the load cell and the setup that we would use for testing, we realized that the values that the load cell is recording, we don't actually know what weight they mean. So right now what we're kind of doing is creating a table to recognize what those values mean in terms of weight. So what I did is I put 50 milliliters through this tube using this syringe like this, and then we got a value from the load cell, and then now we're just going in increments of 50 to get those values pretty much. But, yeah.
Hi, I'm Sajani. Today we're going to be simulating a bladder or a phantom bladder. So far we've done it with air already, and we haven't seen much difference with bioimpedance. As you can see, right now we're very preliminary. We just have a balloon with 3 electrodes, which will connect to this system right here. We have Jesus doing the bioimpedance with his computer software, but now we're going to try doing it with water. So that's why we have this tube. That's what's going to filter our water into here, and we're going to do a little bit of water and then inflate it all the way to 100% maximal capacity and then to 50%, and we'll see if bioimpedance has changed at all throughout that.
Let's put water in it quick. So yeah, it's decreasing way more faster now. Yep, now take water out of it. We should see the resistance go up. That's something.
Let's go.
That's something.
Today we did our preliminary testing using the agar gel for the first time. We were able to carve it out to be exactly 100 millimeters, and with that we just wanted to see if bioimpedance would work.
So yeah, with our tests that we found that once we filled up our little bladder model in our agar gel, the impedance actually dropped a lot when water was in it, and then there was a noticeable difference once we took the water out, how the impedance just picked up right again. So it is promising for feasibility sakes. Now we just have to test it with actual quantifiable data.
It's going to take a while. How long? Okay, so today we actually made a lot of progress on all fields. I started printing 2 iterations of the bottom of our box for the electronics housing, as well as a lid that'll snap on. And then we also printed the first iteration of the bed clamp that the electronics housing will screw into.
I did testing on the flow system. I ran various flow rates to see how accurate the load cell would be. We got some interesting results. We got it's kind of fluctuating a bit, but the average is pretty accurate, so that's good. Having some issues with the testing setup. The pump is not cooperating super well in certain instances at low flow rates, so that has to be investigated. But overall, pretty good success. We're getting a lot of data, so that's good.
So today we both worked on the bioimpedance PVR sensor. In the last couple of weeks we've had trouble with it just zoning out, going 0, but today we were able to use a new and improved mold for it, and the gel this time was a lot harder, so I think that contributed to it as well. And we also incorporated a new technique.
So yeah, this time charge was driving off our data. Now we actually got 3 to 4 test runs that actually worked, and from our first initial looks at it, the milliohms of actual bioimpedance change is like about 500 milliohms, which is pretty consistent throughout all, which is pretty promising. But yeah, from that, what's our next plan? ISR?
Yeah.
Oh yeah.
Yeah.
That's another story.
All right, so this is our uroflowmetry setup right now. We have our drainage bag hanging off of a load cell, which is housed internally in this green box here. In this main housing, we have our ESP32 microcontroller, we have our SD card, and we have our real-time clock for real-time data logging. And we are testing the flow rate right now with this setup over here, which is using a pump and then this very rough pump controller, which we're using to actually test different flow rates and control the different flow rates so we can see if the sensor is being accurate. So over here you can see our little GUI. And so right now we're just going to manually trigger this transmission. And so it'll take a second, but eventually it will connect. Yeah, so it's connecting right now. And now it's a little chaotic because this data happened before and it just kind of sat there. But as you can see, the volume stayed at a solid 100 milliliters, and then it jumped to 200 milliliters. And it's kind of saying the average flow rate is 0.4 because there wasn't much flow. And then this is when we ran our test just now. And this, as you can see, the flow rate jumped up for a little bit, and now it's staying still. And so yeah, it's working quite well. We're getting a little bit of noise here because there was some perturbation in our testing data and how we were dealing with the flow, and we were jostling the bag quite a bit. But yeah, this is how our system works.
In conclusion, our system demonstrates a feasible and continuous monitoring solution that could address critical gaps in urodynamic care. Verification testing has been conducted and demonstrates that volume and flow accuracy falls within a 5% error and can detect changes in real time. Not only that, PBR system can successfully distinguish states between empty, half full, and full states, and is perfectly fitted for our idealized phantom bladder model.
Together, these results highlight a platform that is not only technically sound, but clinically impactful, offering providers with a more reliable, continuous, and non-invasive way to monitor patient bladder function. With further development and validation, our system has the potential to improve patient outcomes, reduce complications, and move urodynamic monitoring into a more modern and data-driven standard of care. Thank you for listening, and we are Team UroSMART.